Let's talk for a moment about limiting reactants. Okay? What's the value of knowing a limiting reactant? First of all, what is a limiting reactant? Okay, the substance, right? It's one of the reactants, so it's on what side of the equation? Left side? Okay, so we have no mercy today. So we have reactants. We have terrible markers today. We have reactants, and reactants combine together to form products. Nothing new there, hopefully. Okay, and when we have a balanced reaction equation, we're given the perfect recipe for producing the product, given the reactants. So written in a generic form, I've done this several times with you. We say A plus B reacts to produce AB. If I have a limiting reactant, that means one of my reactants on this side, right? One of the things that initiate or part of the initial state before the reaction, one of them is limiting. One of them is going to do what? They're going to run out, right? One of them is going to run out. Sometimes you may be told that the other reactants are in excess, which means basically you don't run out. Does it matter how much extra you have of the excess reactants? No. What's going to control what actually happens in the lab is the amount of limiting reactant that you have. Remember, when you do the formula, you write the balance formula. That's the hypothetical. That is the best possible perfect recipe mixture you have. Now, let's say in this example here, we have 2A plus B forms A2B, something like that, right? If I say that B is my limiting reactant, that means when this reaction takes place, B is going to run out first. Which means if I have 1 mole and 2 moles, I'm following my perfect formula to create 1 mole. But if I were to say that this is my limiting reactant, and I were to go ahead and add another mole of A, I still have 1 mole of B. How much product am I going to produce? 1 mole. How much product is produced is based upon the amount of the limiting reactant that I have. If I double this, if I triple this, I mean, if I put 1 drop in a swimming pool full of this, I'm not going to get any more product because I'm going to use up all of my limiting reactant first. This could be just a little bit more, or this could be in excess to infinitum. Okay, you could have an incredible amount of one thing, but you're not going to make any more product because you're going to run out of it. I could pull the Duplos back out of the bag if you want to. I keep carrying them with me wherever I go. But if you're told to build a structure that has 1 red and 1 blue, and you've got 1 red and 1,000 blues, how many 1 red and 1 blues can you make? Just 1. It doesn't matter how much of the excess reactant you have. It's the limiting reactant that determines how much product you're going to make. And so this balanced reaction equation gives us the perfect recipe, the ideal situation, and then we're going to compare that ideal to what actually happens in the lab. Okay? And if we're going to have a perfect reaction with no excess, you know, it's a perfectly balanced reaction in the lab, yes, we would need 2 moles and 1 mole to make 1 mole. But seldom do we have the perfect amount. We're going to have a little bit too much of one thing, or another way to say it is a little bit too little of the others. Okay? So whatever you run out of first, that determines how much product is going to be actually created, not hypothetically created. All right. I mean, other than talking about the different molecular or the molar relationships, one of the other things we talked about is Gay-Lussac or Gay-Lussac, however you want to say it, the French. Gay-Lussac is a way of relating not moles to moles, but relating what? Volumes. In one case is liters. So any volume unit to another volume unit, but it only applies to those reactants and products that are in the gaseous phase. So if they're liquids or solids, you can't apply that proportionality. But if they're gases, you can apply the proportions of gases to gases. Talk a minute about masses. You know, you mentioned doing one of those long problems, those full-blown problems kind of things. That would be, let's say if we were doing the stoichiometry here, and we were going from A across to A2B, we'd have some kind of mole ratio, right? For every 2, we produce 1. And so if we're moving from A to B, the multiple is going to be what? From here to here is going to be times 1/2. Whatever amount of A we have, it's going to produce half as much of the product. And this should make sense. If we had 2 moles of the reactant, we would produce 1 mole of the product, assuming it's the limiting reactant. If we were given how much of the product we had, and we're asked how much would we need to make that much, we would need what kind of a multiple then? Moving from right to left, what would the multiple be? 2. We need twice as much. Look back at our balanced formula, see if that makes sense. If I have 1, I need 2. I need twice as much. Yeah, it makes sense. I need twice as much. But stoichiometry, this molar relationship, or excuse me, the mole ratios can only be used when we're talking about count. Moles means a piece count, right? Individuals, dozens, scores, moles. We've already mentioned, too, that if they're gases, it can relate. If this was a gas and this were a gas, say this one's a solid, can I relate the volume of this to this? No. Why not? This is in a solid phase. It can't relate volumes of anything other than gases. I can relate this to this to this in terms of volume, which would be the same relationships depending upon the direction we're going. But I can't relate volume in any way to B. Nothing to B and B to nothing else. You can't relate them in terms of volume. You still can completely do it with regard to moles, but not volume. And the full-blown problem you referred to is, how do we go from given a certain quantity to the number of moles? We'll learn a couple of other ways later as we progress through the course. But the main one we've talked about right now, matter of fact, the only one we're really dealing with right now, is moving from grams to moles, right? So the way I've taught you in this diagram is to use the space directly below each one of the reactants or products as a place where in the word problem you would write the mass. If you were given a particular mass of reactant A or a particular mass of reactant B, then how much mass of a product could be produced. Right. But you remember that we cannot use our mole ratios with mass. It's not true to say that 2 grams of A and 1 gram of B make 1 gram of A2B. You've got conservation of mass thing going on here, right? It wouldn't work. 2 and 1 would have to equal 3. Otherwise, we've created or destroyed matter. which we can't do in this course. What we've done is built a different structure, which is bigger than these, and so it takes up 2 and 1 to make 1. Why? Because each one of these contains 3 pieces. So when you count up your structures, it still works. That's why we're using moles to moles. But to go from mass to moles, we have to convert it. And we're converting by molar mass. Molar mass in this diagram, think of it as our translation key of going from mass to moles and from moles to mass. Okay. You either have to be all the way through or off. Okay, Aaron? Arms all the way through or off, one or the other. All right, so you have molar mass, and molar mass will move us between moles and grams or grams and moles. So, real quickly then, just to remind us, which direction is which operation? If I'm moving from mass to moles, what am I going to do with the molar mass? So you can divide it by the molar mass. So if I go with mass divided by the molar mass, my result will be moles. So going through this operation will give me the number of moles. The molar mass of what? Well, the molar mass of whatever molecule or atom I'm looking at. The mass of 1 mole, which is the same as the mass of 1 molecule or atom in AMUs, but just simply convert the units to grams. The same number, different units. And conversely, I don't want to just put it on the other side, but let's say we were going from moles to mass, our operation would be multiplication. So here it would be mass times molar mass, right? Oh, excuse me, moles times molar mass. Do it the wrong way. We don't know mass, we're trying to solve for mass. So moles times molar mass to give us mass. The reason I just chose to write both directions here is I don't want you to get confused, and some of you have in the past, that if I'm going from this side of the equation, for some reason I'm always dividing, and this side of the equation I'm always multiplying. That's not the case. This process uses the idea that if I'm moving from moles up, I'm multiplying by molar mass. In any case, here, here, or here, if I'm moving upward, I'm multiplying by the molar mass of whatever the molecule or element is. Moving up, I'm going to multiply by the molar mass. Moving down, I'm going to divide by the molar mass. So once I take a mass, create a molar mass, or excuse me, take a mass, calculate the number of moles, take the moles, relate it to another number of moles, take the moles, multiply it by molar mass to take me back to mass. And that's the full process. There's really nothing more to this module than understanding this diagram. So you've got to be able to go from, given a mass, compute the molar mass, divide the mass by the molar mass. Let me just write it as mass divided by molar mass, which will give me the moles, times a mole ratio, which is this multiple in the middle, which will give me a number of moles. Then I'm going to multiply that by the molar mass, and that'll give me a mass. Step 1, step 2, step 3, step 4, step 5, step 6. This is the full-blown problem you referred to, from mass to mass. What we may get is given moles and asked for moles. That is all step 4. Step 4 is moles to moles. That's just using the mole ratio. I guess you could say down here too, we need to compute a second molar mass, right? I'm sorry. Let's make it 7 steps. So we have to compute the second molar mass. We're going to do the mass times, or excuse me, the moles times molar mass, and that's going to give us S. And there's never deviation from what we've learned so far. Where we're at in this course, this is the process every single time. Just do it in order. This will be the mass that's given. This will be the mass that we have computed. A given mass for a molecule, compute the molar mass of the molecule, take the mass divided by the molar mass of the molecule. That'll give you the number of moles. The number of moles times the ratio, compute the molar mass of the, let's say it's the product. I don't want to limit it to that, so I'm going to take that back off. Let me second guess that. Moles ratio, compute the molar mass. This is, let's say, of the known. Molar mass of the known, molar mass of the unknown. Take the number of moles, multiply by the molar mass, and the mass computed of the unknown. Anybody see anything else that might be helpful in clarifying the process? Okay. So this process right here on our diagram is when we're moving down from mass to moles. Then we have the mole ratio, pure stoichiometry here. Then this part is when we're moving in our diagram from moles back up to mass. It's done in this order, but in our directions, it takes us from moles to mass. Any other questions for me? Yes? What might that be? Anything in this module? Okay. Decomposing unknowns. So it's kind of towards the end, the last section or so of the course. All right. Why don't I go ahead and walk through 8.10 and 8.11 again? Okay, since we did, this is probably the least amount of information we've done in class on this type of problem. Is everybody done with the process here, or do you need it for a little bit longer? I'll leave it for a bit. Okay. I'll try to work over here on this side of the board for a bit. All right. On your own, 8.10 says, in one experiment, the empirical formula for a compound is determined to be NaPO4. Now let's just think about this for a minute. It says the empirical. Again, I just made this up on the fly the other day in class, and I wrote beside that E. I circled it. Empirical. What does it mean that this is the empirical formula? Would I go to the lab and try to make this particular molecule? No. Empirically, what this is saying is, I know that whatever the combinations are, this molecule has 1 sodium, 1 phosphorus, and 4 oxygen in some multiple. It could be Na1P1O4. It could be Na2P2O8. It could be Na3P3O12. It could be some multiple of that. But this is how they combine. They combine together as a 1 to 1 to 4. Okay? Probably what happened is whatever method they use, like if we're working at gases, they went through and said, hey, look, at when I'm making the gas in this reaction, I have a volume of 1 to 2 to, they parse it all out. We're not going to worry right now about the actual technique in the lab to determine this. There's several different ways to do it. But however they came about it, they're telling you, hey, in the lab, empirically, you determined the formula was NaPO4. Then, it says in a separate experiment, you're looking at the same molecule, but in a separate experiment, its molar mass was determined to be 354 grams. Okay, its molar mass is 354 grams. What is its molecular formula? Molecular formula is exactly how it's constructed. The exact number of each element, not its ratio. This is the ratio, 1 to 1 to 4. Now we're trying to figure out what's the actual formula. So, what is going to be our first step then in solving this type of a problem? Let's go find the molar mass of the empirical. Okay? To find the molar mass of the empirical molecule, the mass of the molecule would be equal to the sum of the masses of all of the components, right? So we're going to go through and look at sodium, phosphorus, and oxygen and compute what would be the mass, the molar mass of the empirical molecule. So let's add them up. The sodium, 0.0, okay. Phosphorus, and oxygen should be 16. And remember, we're going to do this by adding them up, which in this case it won't matter because it's all 2.0 anyway, right? Because there's 4 of them. So 1 sodium, 1 phosphorus, and 4 oxygens. So we add them up. Let's add up the zeros. When you add up all the zeros, you get 0. Okay, good. Okay, 3, 4, 10, and 18 is 28. 2, 4, 5, 6, 7, 8, 9, 10, 11. So, because this is the empirical, it could be the molecular, right? It could be. I mean, we're saying empirically it's NaPO4. Molecularly, it might also be NaPO4. But if it were NaPO4, what would its molar mass be? It'd be 118 grams per mole, right? But that's not what we have. We've been told that from another experiment, we've determined that the molar mass is 354 grams per mole. And we know that since it's not the same, that this is not also the molecular, this is only the empirical, and that the molecular must be some number of multiples of this. Because it's either going to be one set, or 2 sets, or 3 sets, or 4 sets, or 5 sets, or whatever, but it's going to be an even number of sets of this ratio. So, if the empirical is 118.0 grams per mole, and I know that I've been given from another experiment that the actual molar mass is 354 grams per mole, what am I going to do? Just take the computed, I've been told it is 354 grams per mole. I know the empirical is 118 grams per mole, right? Those will both be 0.0s. I just dropped them, okay? It's going to give me a ratio, right? It's going to give me a number when I do this. If I take my actual divided by my empirical, the result is going to be 3. 3. My actual is 3 times as massive as my empirical. Okay? My actual is, I'm going to go ahead and erase this now that we know it's 118. That's how we computed it. Okay? My actual is 3 times. Now, one way to think about this, I'm going to write something on the board which is not technically right, okay, but I want you to understand the idea. If I had one of them, this would be the formula. What I'm saying is, I've got 3 times as much of every one of them. If this was just a math problem, I would go 3 times that much, right? in terms of its mass. I need to be this ratio, and I need to be 3 times as big. How do I get that? I multiply it by 3. But in chemistry, if I just put a 3 in front of it, I've got 3 times as much stuff, but I don't want just simply 3 times as much stuff. It needs to be 3 times as much stuff contained within that one molecule. So I can't do this. But since I'm computing the actual formula of a single molecule, this is one of those rare exceptions where, yes, now we actually have to mess with not the coefficients, but we mess with the subscripts. And so I need 3 times as many sodiums, so I need 3 times as many sodiums. And I need 3 times as much phosphorus, and I need 3 times as much oxygen. Okay? So, and this is one of those things where if you were to say, okay, how many sodiums are in the actual molecule? Well, 3 times as many was in the empirical. How much phosphorus? 3 times as much that was in the original empirical. How much oxygen? 3 times as much oxygen as was in the empirical. But hopefully we're savvy enough now that we recognize, hey, this is a polyatomic ion, right? Sodium phosphate, it's a PO4 molecule, or excuse me, PO4 polyatomic ion. It's ionically bonded with the sodium. And so it's okay for me to do with the Na3, but what's more accurate over here would be to keep this as a PO4 molecule, or excuse me, polyatomic ion. And how do I get 3 times as much? I'm just going to subscript this with my 3. Okay. So if on the exam, for example, if this were the question, if you were to come back and say it's Na3P3O12, yes, that's true. In this particular instance, hopefully by now you'd see, hey, but it's a polyatomic ion, and that's going to stick together, but I need 3 of them, and I indicate that by subscripting this with a 3. If I look at this, I've got the same number of sodiums in this line as I do in this line. 3 sodiums, 3 sodiums. How many phosphorus do I have? 3, 3. How many oxygens? 3 sets of 4, which is 12, 12. These two things are saying, hey, I need the same building blocks. This just shows a little more savvy in how it's constructed. Okay? Frankly, at this point in the exam, or this point in the course, if you give me this, you're going to get credit for the question. Okay? Don't stress about this, but I would hope maybe I'll give a bonus or overlook another malady, okay? If you were to actually go, wait a minute, but I see a polyatomic ion there. I'm going to take a shot at this. It wouldn't just simply be P3O12. It would be PO4 sub 3. But the process, again, steps in process. Here we've got steps in process to do our big stoichiometry problems. Here we have steps in process to go from an empirical to a molecular. This right here is the molecular. So we have our, let's see if we can come up with some steps. We have the empirical. Got to spell it right. Empirical. Come up with the molar mass of the empirical. 3. The molar mass of molecular divided by the molar mass of empirical, which is going to give you a ratio, right? And then we're going to multiply. We'll say that produces a factor. And then the empirical times the factor. Okay? When I say empirical times the factor, that's why I nuanced here. We're not just simply going to take the empirical here and multiply it by the factor by sticking it out in front. That's not the way I mean to apply it. What I mean is taking the empirical and applying the factor to every individual atom. Okay, that's a little different than the way we've normally thought of it. Normally we've come up with a factor, we've multiplied the whole molecule by simply putting that number in front of the molecule. But here we're trying to determine the molecular formula of one molecule, not three of one molecule. And so we would actually apply the factor to each individual atom. Okay. Now the next question, that's 10. Any questions then on this? Did that confirm a process for some of you? Or maybe give a process for you if you didn't have one before? Okay. Okay, so we've given an empirical. We compute the molar mass of the empirical, which we did before as being 118. We take the molar mass of the actual molecule that we've been given in the problem, divide it by the molar mass that we've computed for the empirical, and that gives us a factor. In this case, the factor was 3. Right here, this is that step. Then we take that factor of 3, and we multiply the empirical by it, but not by putting the coefficient in front and saying we're done, because all of these have to be used up within one molecule. So what we have to do is apply the factor to each individual atom from the original. 3 times as many sodiums, 3 times as many potassiums, and 3 times as many oxygens. In the same way, I'll try to work a little lower here and leave this on the board. For 811, it says that a compound, whatever it is, compound AB, decomposes. Now, you should know that decompose means what? Doesn't get icky and slimy, right, and stare at you with a funny face. Okay, decomposes means it's going to break down into its constituent elements that made it up. In this case, compound is decomposed into 28 grams of sulfur and 27.8 grams of oxygen. What's the empirical formula over here? Let me ask you a question. Is it true that I had 55.8 grams of whatever it is? Yeah, we can do that. Conservation of mass, right? I've got a certain amount of mass, produces a certain amount of mass. That doesn't mean it's going to relate to moles, but I can do mass to mass in that way. I'm not relating using stoichiometry. I'm just relating, hey, if I start with a certain amount of mass and I break it down, I'm still going to have that much stuff at the other end. But rather than it just being generically AB, now as I look at it, I say, hey, it's not just AB, which are whatever, but it's actually sulfur and oxygen, right? I got sulfur and oxygen that make it up. So I'm going to get rid of AB, and I say it's going to be some number of sulfur and some number of oxygen. Because it was generically before just AB, but now, no. In order to get sulfur and to get oxygen, I have to start with sulfur and oxygen. And since I'm starting with sulfur and oxygen to end with sulfur and oxygen, now I've got something I can work with. I've got 28 grams of sulfur and 27.8 grams of oxygen. The question now is, how many were in my original molecular formula? Now we're not talking about how much stuff in terms of its mass, but how much stuff in terms of its count, right? How many in terms of counting them up? Can we use grams directly to figure out how many there are? No. We've got to go indirectly. In this same way here that we went indirectly. I've got 28 grams of sulfur. If I'm going to relate pieces to pieces, I'm going to drive toward what units? Moles. Good. Good. We're going to moles. Don't mean to sound shocked, but we're going to moles. Okay, so looking at sulfur, we need to take 28 grams now and say how many moles of sulfur is that? Looking at the periodic table. It has a atomic mass of 32.1. Right? That's 2.1 grams per mole of sulfur. and oxygen, which still should be always 16, good. So 16.0 grams per mole of oxygen. What would it be per grams of mole for O2? How many grams per mole? 32, right? So we need to remember that little caveat there. 16 would be for O, just simply O. But we're producing O2, so it's 2 oxygens, or it's 32.0 grams per mole of O2. Now, if I take my mass and I divide it by my molar mass, my product is then going to be moles, right? So anybody with a personal computer here, what's 28 divided by 32.1? Just give me, is it 0.872? Yeah. Okay, we'll just go with that. How many should we, let's look back up here. We've got 1, 2, 3 divided by 1, 2, 3, 3 significant figures, 1, 2, 3. So hopefully the next line over here is 4 or less. Okay, 2, okay. So we have this many moles of sulfur, and what's 27.8 divided by 32.0? Okay. Okay. So, whatever it is in terms of the number of moles of sulfur and the number of moles of oxygen, I look over here and I see that what I actually produced were this many grams, and I divided it by its molar mass to say I actually produced this many moles of sulfur and this many moles of oxygen. Now, most problems we've done up to this point, you had nice full integers, right? No fractions, no decimals. It was like 1 to 2, 2 to 4, 7 to 32, whatever the numbers were. Now you've got something that's 0.872 to 0.869. How do I relate those two things? Process-wise, what am I going to do? Go ahead. Divide it by the smallest one. Good. But here's the deal. Look at between 0.872 and 0.869, they're about the same, right? You're going to be off by like a couple thousandths. So, knowing that, if I were to go through and divide each one by the same, we would know that we have a relationship of 1 to 1. Right? Well, let's say that we're dividing by 0.869. This would be 1 and some probably 100 thousandths of something. And this is going to be 1. So we have basically a 1 to 1. How many sulfurs do I have on this side? For every 1 sulfur, I have how many oxygens? Pardon? I have 1 set of 2, right? So I have one sulfur and 1 set of 2 oxygens. How could I get that from this formula? Only if sulfur were actually 1 and oxygen were actually 2. Because if sulfur is 1 and oxygen is 2, I can break it down into 1 to 2. And this is the empirical, right? This is the empirical formula for this molecule. Because it's empirical, does that mean it could be simply SO2? Yes, it could. But what could it also be? S2O4, S3O6, S4O8, S5O10, S6O12, and on up, multiples of those proportions of 1 to 2, all the way up. What would I need to know in order to find out what it actually is? I know somebody said something, I didn't. Molar mass, right. If I knew the molar mass of the actual, I could do this problem then. I could say, hey, the molar mass of my actual is a certain amount. The molar mass of an SO2 is a certain amount. What is my factor? If the factor is 1, then I know it's this. If the factor is 2, it's S2O4, and so on.